In this video, we're going to talk about momentum as a derivative. And to do this, we're going to use a momentum versus time graph to help us kind of wrap our heads around what it is, what this derivative is. So draw a momentum versus time graph and then graph some random line. Then we are going to indicate the slope of this graph. So we're going to have some change in t and some change in momentum, which we can call change in p. Now remember that this can also be written as m delta v because the mass times the change in velocity. Either of those things is appropriate. Now the rise over run, the slope, is going to be the change, we'll write this over here, is the change in momentum p over the change in time. Well, this should look familiar now that you have studied impulse. This is a net force equation. Because if you remember, what we did to derive this before was we said, well, normally we say net force is m times acceleration, but that's like saying m times delta v over delta t, which is like saying change of momentum over change in time. Okay, so on a momentum versus time graph, the slope tells us the net force that acts on an object. Now, slopes are derivatives. And if I think about not the finite change, but instead the infinitely small change, or the dt, the infinitesimally small change, and then the dp, then I'm going to get that the net force is equal to dp over dt, which is our equation for the derivative of momentum with respect to time. Let's do an example where we take a look at a graph and need the slope to find force, then a problem where we're given a momentum function and we need to take the derivative to find force. The vertical momentum of a small rocket is shown on the graph below. What is the net force acting on the rocket in the first 3 seconds? When is the rocket in equilibrium? And what is the net force on the rocket at 10 seconds? Okay, so hopefully you've taken a second to sketch this graph, and let's go through parts A, B, and C one by one. So in the first 3 seconds, this section right here, if we want to know what the net force is, then what that means is we want to take a look at the slope of this entire section. If this was a curving line, then we couldn't say what the net force was during all of those moments. But since it's a straight line, then that means the slope is constant. And all I have to do is figure out what delta p and delta t is at any moment. So I can just pick 2 points on this graph. Let's pick here at the beginning and here. That sounds really easy. Okay, so the change in momentum over the change in time. From 0 to 1 seconds, so that would be a change of 1 minus 0, or 1 seconds, I go from 0 to 10 kilogram meters per second of momentum. So 10 minus 0 is 10 kilogram meters per second of momentum. Well, that gives me 10 kilogram meters per second squared, or that's a Newton of force. Okay, great. When is the rocket in equilibrium? Well, the rocket is in equilibrium when the net force is 0. Remember that that's what equilibrium means. And so I'm looking for a section where the slope is 0. And that would be this section, that would be this section from 3 seconds to 7 seconds. Here the slope is 0. It's flat the entire time. So 3 to 7 seconds. Okay, C, what is the net force on the rocket at 10 seconds? Okay, so notice at first we say in the first 3 seconds, so the fact that this is a constant slope the entire time tells me that this 10 newtons of force is there the entire time. Well, now it's asking me at 10 seconds, so really all I need to do is figure out what the slope of this line is, because also it has a constant slope, and I just need to figure out what the slope on any point in the line is to know what it is at 10 seconds. So the net force is the change of momentum, which in this case, the change in momentum, here, let's pick just the 2 endpoints. That seems easiest. I go from 30 to 20, so the change of momentum down is a negative 10 newtons. And the amount of time, we go from 7 to 12 seconds. So the change in time is, what, 5? Yeah, 12 minus 7, so 5 seconds. So the net force is negative 10 newtons over 5 seconds, or negative 2. And actually, I wrote the units wrong. Our y, is kilogram meters per second. So kilogram meters per second, which gives me kilogram meters per second squared again, or you could call that newtons. Okay, so now we know that the net force at that section is negative 2 newtons. All right, now let's try a problem where we have to find the derivative. You program a toy boat so that its momentum obeys the equation P equals beta t cubed plus alpha t plus 10 kilogram meters per second, where alpha is 4 kilogram meters per second squared and beta is negative 2 kilogram meters per second to the fourth. What is the net force acting on the boat at 2 seconds? Okay, so let's start by writing for ourselves an equation that we want. And we want an equation to find force, right? So we know that the force is going to be equal to the derivative of the momentum equation with respect to time. So I'm going to write the momentum equation a bit math friendly. Since it gives me all these numbers, I might want to do this by just plugging in the 4 for beta, so 4t cubed, minus 2t cubed, and then alpha is 4, so plus 4t, that's this section here. And then it gives me 10, so I could just write plus 10. So here's a little math-friendly way to write the equation. And if I want to take the derivative of this function with respect to time, which is going to tell me what the force equation is, then I would take the t squared, and I'd bring the 3 down, so negative 6, then reduce the power by 1, plus 4. This is, the t becomes just 1, t to the 0, so 1. And then 4, and the 10 is just going to go away. So here's my force equation. If you preferred, you can write this as the net force equals negative 6t squared plus 4, which is fine. And to find the force at 2 seconds, then all I need to do is plug in 2 seconds. So negative 6 times 2 squared plus 4. And I would probably write this like f of 2 is going to give me 2 times 2 is 4. So times negative 6 is negative 24 plus 4. So negative 20 newtons is the net force at 2 seconds. Okay, great. Let's do another example. An app on your phone measures your velocity as you skateboard with time. The combined mass of you and the skateboard is 65 kilograms. Okay, so here we can talk about the relationship between momentum versus time graphs and velocity versus time graphs. Momentum is just mass times velocity. So if you take this 65 kilograms and multiply the momentum side or the velocity side, then you get mv, or the velocity. So in these questions, I'm going to be looking at the change of velocity, or the slopes, but I'm going to have to interpret it to end up getting what the force is. So let's take number 1, for example. What is the net force acting on the rocket in the first 3 seconds? Okay, so similar to what we were doing before, if I find the slope of this, what I'm going to be finding is the change in v, that would be delta v, and the change in t. Okay, so the change in v over the change in t. So let's figure out what that is. Well, the change in velocity, I go from 4 to negative 6, or you could pick any 2 points on this graph, is fine. I'll just go ahead and do that. 4 to negative 6 is negative 10. And the amount of time is from 0 to 3, so 3 minus 0, or 6 seconds. Okay, so that's the change in velocity over the change in time. How do I use that to find the net force again? Well, that's acceleration, right? And so here we have that multiple expressions for force. The net force is what we've been saying for this set of problems. The change in momentum over the change in time, well, that's like saying m delta v over delta t, or m times a, the acceleration. So you can do whatever you want. Basically, I'm just going to be multiplying my equation by the mass, and I will get my net force. So 65 kilograms times that negative 10 over 3 is going to give me negative 650 over 3, which is going to give me negative 216.6 repeating. And again, the unit is kilogram meters per second, so meters per second squared, or we consider that to be a Newton of force. So again, all I had to do was take a look at the slope of the section of line, except I had to recognize that because this is a velocity versus time graph, I needed to multiply my answer by the mass in order to get a force for this problem. Okay, when are you in equilibrium? Well, here I don't even have to do any math. I just recognize the fact that if I have no slope, then when I multiply it by 65 kilograms, I'm still going to get 0. So that is the section from 3 to 7 seconds again. So here, again, your net force is 0 from 3 to 7 seconds. Okay, good. C, what is the net force on the rocket at 10 seconds? All right, same thing. So I'm looking at the slope of this section, right? Because the slope is the acceleration, and mass times acceleration is the force. So pick 2 points. Are there any convenient points? You know, there really aren't convenient points. Let's pick the ends. Okay, here and here. Change of time, delta t, from 7 to 12 seconds is 5 seconds. And now I have an increase, my delta v. I go from, looks like negative 6 to positive 6. So that's a positive 12 meters per second. Okay, so the net force, m delta v delta t, so 65 kilograms times the change of velocity, which is a positive 12 meters per second, over the change in time, which is 5 seconds, is going to give me a positive 156 newtons. So that's the net force at 10 seconds. And also, again, because this line has a constant slope, that's the net force at any moment in time from 7 to 12 seconds. All right, let's do one more derivative problem. A 2 kilogram remote control car's velocity is given by v equals at squared plus bt plus c, where a is 3 meters per second cubed and b is 0.5 meters per second squared. Oh, you know what? And I think we need to be told what c is. Let's say that c is 4 meters per second. Okay. What is the net force at 10 seconds? So in this problem, remember before we said that the net force was the derivative of momentum with respect to time. Well, in this problem, what we're given is v. And what I can do here is I can think about v as a momentum equation if I just multiply that velocity equation by m. So let's do this whole thing symbolically, because that comes up from time to time. How would I do this symbolically? Well, now my velocity equation would look like this. V equals mat squared plus mbt plus c, where m and a and b and c, those things are all constant. They're not changing in the problem. Sorry. We would write this as p. That's our new p equation. So how do I get the net force? Well, I just take the derivative of that equation with respect to time. So m and a is constant. It doesn't change. I'm going to get 2 ma times t plus this just becomes mb, and c goes away when I take the derivative. So boom, there's my force equation. And if I want to find the net force at 10 seconds, then I just plug it in. So the net force at 10 seconds is 2. Now I'm going to do 2 for the mass, 2 kilograms. A is 3. T is, 10. The mass is 2. B is 0.5. And I get that the net force is 120 plus 1, or 121 is the net force at that 10 seconds, newtons of force. Okay, great. So in this video, you learned that momentum can be graphed with time, and the slope of that graph tells you force. Now, we can just look at a graph and find the slope to be able to answer questions about force. If we're not given a graph and instead we're given a function like this, then we can take the derivative of the function of momentum with respect to time to give us a net force equation. Sometimes we have to change our equation slightly if we want it to look like momentum by multiplying by mass. It's pretty straightforward. Okay, you are super smart, and this video is done.